So yes, my name is Andrew Johnson. This is the first of our 2015 lecture series. Following this lecture, we'll be going into things like asyn and area detector and more end-user specific stuff. But for the basis of those as to how the IOC actually talks to its hardware, we'll be going through this lecture on writing device support. So this lecture basically covers, it's an overview of the concepts behind device support routines, and the terminology here, this is Eric Norham's terminology. He calls this the stone knives and bearskins approach because there are much easier ways of actually doing this where there's a lot less software you need to write if you're making use of asyn. So the asyn framework simplifies a lot of the work associated with here, but asyn is basically doing everything that we cover in this lecture. So behind the scenes, this is how device support work, and the concepts that we're talking about here still apply to what we're to even asyn drivers. So in outline, then, I'm going to be covering what actually is device support. And how it connects to the IOC, which is the DBD file entry and the device support entry table. We'll talk about device addresses, the link addresses that we use to actually point to particular pieces of hardware we want to interface to, the various different support routines that have to be written as part of the device support, how you go about writing code that uses interrupts or some other way of basically letting the IOC know that there's new data around. And we'll talk about asynchronous input and output and the use of callbacks. So device support then, it's the interface between the record, the building block that we actually instantiate inside the IOC, and the piece of hardware. It doesn't actually have to be hardware, of course. It could be some other piece of software that's not EPICS specific or that's not directly connected to the IOC, but you want to interface through the IOC. So device support then, it's that interface, and it's implemented as a set of routines that the record support calls. The record type itself determines what routines it's actually looking for to call. And the code within the device support that you write has full read and write access to the record field, so you can actually override some of the things that the record does in certain circumstances if you need to do that. The device support determines whether a record is synchronous or asynchronous. Those of you who were in at the lecture where we talked about the principles of the IOC database, there's this distinction between synchronous records where the results of the I/O are available immediately within a few tens of microseconds at most, or a slow device, a network attached device, or a serial attached device where it takes a lot longer for the I/O to actually happen, and there you have to use the asynchronous interfacing. So we'll talk about how that applies to device support, and how device support is actually responsible for determining on a particular I/O basis whether this is a synchronous or asynchronous operation. And so the device support actually then does actually do the I/O operation. It performs the record, performs the input or output as the record is requesting for it. And if it implements interrupts, I/O interrupts, then the device support provides that mechanism to actually implement that. Why do we use device support? You could consider that instead of having this extra layer, you could actually write a different record type for each hardware interface, which gives you more flexibility to add fields that are specific to a particular record type and so on. We have actually done that in the past. There are certain vacuum record types which are specific to a particular vacuum gauge or that kind of thing. But we find that a separate device support gives us various advantages. You don't actually have to learn the specifics of a particular record each time. You just learn the specifics of the generic record types, and then you can you know how to use those. So we've got more modularity. If you need to make a change to the hardware, so you're pulling out one particular kind of motor and plugging in a different motor controller, you can use exactly the same motor record definitions. You just need to change one or two fields to actually say, oh yes, we've switched the hardware, it's now one of those, not one of these. And we also have a better separation between the code that actually talks to the hardware and the record API, so that you don't have to write as much code to talk to different kinds of records. And asyn actually makes this even more flexible, because you really only have to write certain interfaces, and then you can talk to that particular device from various different record types that use the same device interfacing. But you can, of course, write custom records, and you can do that, and various people actually do in certain circumstances. As I said, we sort of discovered that you really, really, really need to do that. You might want to avoid it otherwise, but there are places and times where it's appropriate. But most of the existing record types seem to be sufficient for most of the applications in our experience. How does a record talk to the device support? So this is the sort of where is the connection happening between that? And at the level of the guy writing the application code, it's all done through the DBD file and specifically through the device statement that appears in that DBD file. So an application database file says, I want the device type of this record to be my devsup, my device support, my particular device. That's a string. That string gets looked up in the list of device support entries, the device entries in the DBD files that the IOC loads. So the my devsup matches my devsup as the final argument to one of the device statement entries. And it's also specific to the record type, the first argument in there as well. So the third argument then is the name of a symbol, a C symbol, which is actually compiled in. So the device support C file on the right-hand side there, you see we actually declare my dev set, and we put it in an EPICS export address statement. That makes it available to the AOC at boot time, so that when it loads the device statement that says you need to use my dev set, it can actually look up and say, oh, I've got that symbol here, and then hence it can point to the device support entry table and find all the routines that it needs to deal with it. I'll go through all the details of this in later slides, but this is the sort of the overview as to how you actually make the connection between the record and the particular piece of hardware you want to talk to. Or the particular driver for that piece of hardware, at least. So the device entries then, there are 4 arguments that the IOC uses as part, or loads as part of that DBD file. The record type, there has to be a device entry for each record type that you're supporting, so there'll be one line for every record type, one device line for every record type. The address type there specifies what kind of information the device needs to find the particular device, and we'll come back to what those address types are in a minute. The dset name, as I said, is the name of the device support entry table found in the driver code, and by convention, the names that we use for that, this is a global symbol, so you can't just say my dset and expect it to not necessarily clash with somebody else's my dset. So the convention that we tend to use is to include the record type name and the hardware type. So dev AI DG535 would be a device entry, the dset for a device entry for an analog input record talking to a DG535 module, and so on. So that's just a convention. You can change that and do other things, but that's what most people will expect if they actually need to look at your code and to understand it. The device support entry table then is a C structure that is declared within the code itself, and it contains pointers to functions that the record type and the IOC can call to do certain things for the device support to actually perform the operations. The specific list of routines in that device support entry is dependent upon the record type, but there are a common set at the beginning. And so each device support layer, each record type really defines what those set of routines are. And this is the structure definition, the sort of thing that we see. The first one is a number which is usually the number of routines for this particular record type. And the record type usually checks that number, so it's just an integer, and it's usually going to be 4 or 5 or something like that. And then we follow that by a series of routines. So these are the standard routines that all record types and the IOC needs. A report function, which gets called when you do a DBIO report so that you can actually see what's the current state of your driver. An initialize function, which gets called twice at startup when the IOC boots, once before the records have been connected up, all the links are connected, and the records have been fully initialized, and once afterwards. So pass is either 0 or 1 there. And often you'll find you're doing things in the initialization routine only on the first pass, so only when pass equals 0. Right? But there are certain cases when you need to do things when pass equals 1. So that's how you can distinguish. And then for each record, so that initialize routine is called once for the whole device support layer, and then for each record, the device support gets called with a pointer to that particular record. So the structure that points to your record is passed in, and the device support can then look at it and do what it needs to initialize. And it can then look at the hardware address and say, do I actually have a piece of hardware at this address, and so on, do any checks that it needs. The fourth routine there, get IOINT info, we'll come back to later. That's associated with the interrupt support, and that's how the IOC knows whether the particular device support can support IO interrupts. And then after these 4 routines, then there's almost always one more routine, which is the read and write routine. There may be more than that, depending upon the record type as to what it actually needs. So the number then specifies, as I said, the number of pointers that you actually got in this that are defined in this particular device support. If you don't have to use all those routines. Quite often there is no report function in some of the device supports. Although I would encourage you to write one, because that's actually a good place to put debugging information. But you don't have to, so that you can put null pointers in any of these if you don't actually want to provide them. And the other thing is that these structures, the instantiation in your code is usually static because of the EPICS export statement that we'll see again later, that I showed you on an earlier slide. That actually makes a new symbol name. So these things are don't need to be globally visible because of that EPICS export that handles all that for you. So that initialize routine then, I said this is actually responsible for initializing the device support layer. So if you need to allocate memory on a global basis for the whole thing, say you're talking to an external library, this might be the time when you initialize the interface to that library. You basically say to the library, hello, I want to talk to you, wake up and do any things that you actually need. At this point, you don't know what hardware devices you have, so you can't actually say, I want you to connect to this device or that device. But if you do have one-off startup operations, you need to start a background task or something like that, or create shared tables. And as I said, this is called twice. Pass 0 happens before any record initialization has happened. We don't know any address information, so we can't do anything at this point. But in pass 1, this has happened after all the record initialization has gone, so we've actually called the init record routines, which we'll come to in a moment, already. So this can be a final, okay, I know all the hardware I'm talking to, now I tell my thing to actually go ahead and kick things off. something like that. You can use it as a final startup type layer, type routine for that. You do now know what all the devices are that you're talking to, at least at initialization time. The init record routine then is the one where it's called once for each record that is actually requesting the use of this particular device support. So the dtype field of that record matches this particular device support, and obviously the record type is the same. This is an optional routine, but usually it's there. I have written routines that there are device supports that don't use one of these, but usually you're going to want to check the input or output hardware address and maybe try and talking to the hardware to see if it's actually present and give an error if it isn't, that kind of thing. But there are some devices that don't need that. So it's an optional routine. Usually it's going to validate that input or output field, check that the hardware is actually present. It may allocate storage if it needs to use. It needs some memory to store stuff to actually be able to talk to the hardware or a driver layer that it's talking to. There is a field in every record called dprivate, device private, which is available for device support. So it's a void star pointer, and you can allocate memory and stick a pointer to that memory in this, and that's actually used by most device supports. Will tend to need one of those. You can, in this routine, you may be programming device registers or actually setting up network connections, those kinds of things, and setting any record-specific fields for conversion between engineering units. So as part of the analog input record or analog output record, you may know that my device is a 12-bit ADC, so you need to check the linear field and set the eSlow and eOff from eGUL and eGUF for those engineering units conversions, based on the conversion between the engineering units and the raw hardware units that you're going to be talking to the real hardware with. So those kinds of things happen in this routine. Now we get to the actual read-write, the real I/O operation, and that gets called whenever the record is processed, and is actually called from the record's process routine itself. So it actually performs or at least initiates the I/O operation. So assuming that we are using synchronous, a synchronous operation, so we can finish this operation immediately, then an input, a read routine, is going to copy the value from the hardware into the record's raw value field, and it will usually return 0 at that point, which says there's a value, I've got success. Or it may, if it reads an engineering unit's value directly, say, then it may return the value 2. That's analog input record specific, but the return value tells the record something about the conversion, about the value that it's got. For output routines, a write routine, then it's going to take the value from the record's raw value field and convert it, send it to the hardware somehow, put it in a register or whatever it is, whatever it has to do to actually update. And again, it will usually return 0 to indicate a success. It can also set, in this routine, you may also, if you have problems doing the I/O, you may set alarms and so on, those facilities inside the record. I won't go into detail on those in this lecture, but examples of those are available in most of the device supports that you guys can look at. So we're looking at device addresses here, and actually I went into the detail as to what all the different device addresses and address types were in the IOC database principles record. In this particular case, the address type, the second argument to that device entry table, specifies what kind of hardware address we can talk to. So the addr type there, the device example here for the XY240, that second argument is VME_IO, and a VME_IO means that the binary output record's out field is actually a structure with a series of fields. One of those is the type, and so the type will be set to the constant value VMEIO, and then so your device support is going to want to check that the type is the type it's expecting, and then if it's a VMEIO, it's going to have the value itself is going to have three fields. The card number and the signal number, which are both 16-bit integers, and a string, which is the final parameter, which is available to you to use and to parse as you wish. VMEIO is probably one of the main address types that we use. Instrument I/O is the other one. The instrument I/O is basically almost the same as that, but there's no card and signal number. We have talked about these in the past. The Application Developer's Guide describes all the I/O types and what all the different fields are that are available. As I said, most cases, VMEIO or instrument I/O are the main ones that gets used. And the instrument I/O is basically completely generic. The IOC doesn't know anything about the contents of the address, and it leaves all the parsing up to the device support. So that then the device support will be looking at that inside its init record routine. A simple example, two-page example of a device support. This one is designed for VxWorks or RTEMS because you've got memory mapped I/O, so we can actually access the hardware value directly. So this is a binary input record device support. We need to pull in a few header files, rec global, devsup, devlib, and the BI records, so we know what the record structure looks like, and we have to include EPICS export. Our init record routine takes a pointer to our record, and as part of that, what we do, the first thing is we actually check that our input field has the address type VMEIO. And if it doesn't, then there's probably something wrong in our DBD files, so we need to give an error there. But basically, we want to assume, we check that we've got a VMEIO, and in this case, we're also looking to see that the signal number is between 0 and 7. If it's not, then there's a problem, so we actually put the record into an alarm state. Actually, no, we don't put it in an alarm state, but we just return an error, and that will print up an error on the console as the IOC boot up, basically saying we have a bad input. Next, we come to the dev register address line, and the point of this device support, basically, it allows you to specify an address in the VME A16 address space, and so you can specify the address in that space and a bit number. So basically, you can use this to access individual 8-bit registers on any I/O device. So we basically register our address of the card. So the card number in that input address is where we're going to expect the address in the VME A16 space. So I use dev register address. The name is just for reporting purposes. It's an A16 address. We pull the card number out of that input field, and the length, the next argument to dev register address is the length of this particular registration, and we give it somewhere to actually, what's pbyte? Pbyte is a pointer for it to put a value into, or something like that. We check that returns OK and allows us, gives us, and can actually map our register into the CPU space. And then we probe it to make sure that we can actually read from that I/O location. So the dev read probe call, so pbyte is the pointer in the CPU space that relates to that A16 address. And so we do a dev read probe on that byte pointer, and if that gives us an error, then we say there's a problem, there's nothing at that address. If that returns successfully, then we set our device private field, our dprivate, to the pointer, and also set the binary input record has a mask field, which we set to the bit number for the signal number that we were asked for. So that allows the I/O to actually get the data or get the data from that individual bit at the word. So that was the initialization. Now the read routine itself is extremely simple because all we have to do is when we get called to read it, we read the value from the address of our device that we put in device private. So the rval equals star p byte reads the value from the hardware, sticks it in the raw value field, and the record type will take care of extracting that particular bit from given the mask that we set earlier, and so on. So that's all the I/O operation that the device support needs. So most of the work is done in the initialization, and the read is really incredibly fast because all we're doing is pulling one value out of memory. The mask is used actually by the record itself. So we don't use the mask value here, but the record type, the process routine of the BI record, what it does is it takes the rval field contents, ands it with that mask, and then uses the value as a logical true-false value, to set the val field of the BI record. So when we process the BI record, it calls the device support. The device support reads the whole byte into the rval field, and then the record's processor routine then masks off all the other bits and just uses that signal number bit that we specified. And so then the final part of our device support then, at least the C code, is the device support entry table structure. So we're declaring that here, and it's got a report function, which we've set to null. It has an initialize function, which we set to null. There's an init record function, which we provided, so that's the pointer to the init record on the previous page. We're not supporting I/O interrupts here, so our get IO int info function is also null, but we do have a read function. And now notice this read function is static. That's a rather generic name. The init record function here is static. So those names, we can use almost any name that we like for those routines. And this structure itself, the dev bi first, is also static. And that can all happen because of this EPICS export address statement at the bottom, which basically says, what that actually does is it declares another variable which is global. So that is visible, but it is a specific type that the IOC code knows to look for, and so on. So that's basically, you can regard that as magic that we take care of inside the IOC and inside base. So that's basically, those two slides are an extremely simple read device support, input device support. The other routines in the device support entry table, then the report function gets called by the shell command dbior, and the idea is to be able to print information about the current state, hardware status, I/O statistics. You may collect data about how many messages you sent to your device, those kinds of things. It has a level argument. Level 0, the level argument basically controls how much or what information you print out. And level 0, the idea is you should basically print out what hardware you're connected to, but not really any information about that, so one device per line. And for levels greater than 0, then we can put different information, additional information. There are two schools of thought, one of which is that this level may be a page number, so you may have different kinds of information on different levels. Or the other school is that for increasing level, you just add additional information. So that's sort of a choice, but both techniques tend to get used. But it's generally a good idea to put a report function in there. People do like to run a dbior just to see what hardware you're talking to. So for this example, we should probably have included a report function, which would maybe in level 0, it would just say that it's got one, and level 1, it might print out the device address and maybe the CPU as well as the A16 addresses. Then we also need a DBD entry, an entry in the database definition file for our device support. In this particular case, it's going to look something like this. Device we're supporting the binary input record only. We need a VME IO address type. The name of our device support entry table was devbi first. That devbi first matches the name that we put in the EPICS export address and the name of the structure. And then simple input, and that's the string that people would put into their database, the dtype field of the BI records to actually be able to select this particular device support. So here is a database record definition that would use that device support. The dtype is simple input, and our input, in this case, it's actually a template because it's expecting parameters C and S for card number and signal number. If we run that through our application startup script, the application startup script might load that database with DB load records and instantiate those parameters. So it would set the prefix on the name, the card address to OX1E0 and the signal number to 0. And then that would be expanded as by that load statement to give the full record name, test:status bit, and the input. So that would be $C, card number, and then the card address, and S and 0. So that's basically the complete example of that device support from code right the way down to the statement in the startup script to actually load it. Device support is going to want to use various facilities to talk to hardware and so on with an IOC. So you've got your regular ANSI routines. We have some EPICS versions of some of those to standardize things where not all operating systems are quite the same. If you use the EPICS standard IO.h instead of the operating system standard IO.h, then you can we actually replace printf and scanf, and we provide you with an EPICS SN printf, which isn't available on all operating systems. The SN printf is not available everywhere. So, and you can do redirection, the IOC shell redirection then works with the printf if you use this instead of standard IO. We provide the usual string copy, mem copy, and so on, all the usual stuff that are useful, and standard lib available for scanning and so on. There's a library which I mentioned and we showed calls to called devlib, which is an operating system independent layer for doing hardware access. And so there's versions. If you use devlib, your code, if you use devlib and don't try including any operating system specific header files, then you can make code that will compile and run on Artem's, VxWorks, and Linux. And there are places that have Linux VME interfaces, so you can actually plug a PCI card into your PC and connect it to a VME master module and do VME IO from Linux. So if you use devlib, you have the ability to actually access those kinds of things without changing the code. So there's a good reason to use devlib if you can. It means that other people can also take your code and use it in environments where you weren't expecting it to work. And so that provides things like bus address to local address conversions. So where in my CPU space is this A16 address or this A32 address and so on in VME space. It provides interrupt control so that you can enable and disable interrupts and set interrupt service routine things, and also bus probing so that you can see, does this address actually exist? Is there a register? Is there a piece of hardware that responds at this particular address? And then there are also various internal APIs that the IOC, that EPICS provides. EPICS event is for semaphores, a mutual exclusion, so EPICS mutex is fairly commonly used. If you need to generate background threads, then EPICS thread, we have an API for those and so on. and then for sort of the global error and alarm reporting on the records, the recglobal.h provides a few routines and values that you need to use to actually do that kind of thing. Device interrupts we'll talk about then. So if you're writing something for a VxWorks or an RTEM system, you can write your interrupt handlers in C. This is not true of Linux. There things are a little bit more complicated. So interrupts through Linux systems, I would recommend thinking very hard before you actually have to do that. But I believe that some of the solutions do. But certainly on VxWorks and RTEMs, things are very easy. You can write those things in C. And you basically have two parameters for VME interrupts. There's an interrupt level, which is a level between 1 and 7. Old 68,000 base CPUs, you really didn't want to use level 7 because that was non-maskable, and the operating VxWorks didn't like that. But the PowerPCs don't have that problem, so you can actually use level 7 interrupts on PowerPCs. And that interrupt level is often maybe set with ball jumpers or switches, or nowadays they're a bit more software programmable. And then there's a vector as well. So the vector basically says which allows you to specify which routine you can have up to 256 different interrupts in the machine at a time. Although some of those interrupt vectors are reserved, either by the CPU or by the operating system. But so you would basically select which vector to use. And again, that's often programmed in a register, more so than dip switches or jumpers nowadays. So when we're initializing, as initialization, we actually have to basically tell the operating system, connect this particular vector number to my routine, and here's a parameter that I want you to pass into my routine whenever you call it. So you basically call devconnect interrupt VME, tell it which vector number to use, and pass it the pointer to the function and your parameters. But you also enable the particular interrupt level. So the levels are shared between different pieces of hardware, and the vectors are usually specific to a particular device, although on PowerPC you can share vectors as well, but then you have to be prepared to do that. But you have to enable specific interrupt levels onto the CPU. So that's why you need to know for a particular device what its level is, as well as what vector number you want it to use. Often you can program the device with the vector number, but you may not be able to set the level. Within the record processing, then, the record for I/O interrupt, the idea is that the record should be processed whenever that hardware interrupt actually occurs. The granularity of interrupts, how many interrupts there are, depends upon the particular software, the device support, and the hardware itself. So there are some devices may have an interrupt per channel. Others, like the Zycom XY240 binary input TTL I/O module, I think that only has one interrupt for every 8 bits. So you basically only have one interrupt source for 8 possible signals. So that's what I mean by the granularity. Nowadays we tend to try and distinguish. So even if you only have one interrupt source that's shared by 8 signals, you may look and say which one of those signals actually changed, and then only trigger. So in software, you would then determine which of the particular signals it is that you need to process the record for. But you can also basically say, I've only got one interrupt from this device. I'm going to process all the records that are connected to that particular register, and they can work it out for themselves whether the value changed or not. So that's the distinction between interrupt per channel and interrupt per card. You will need to include dbscan.h to get some additional declarations for this. And then the idea is that at initialization, you call scan IO init once for each interrupt source. So that whether that's per channel or per card is depending upon the granularity that you're implementing. But you call scan IO init once for each of those interrupt sources. And then your device support entry table provides a get IOInt info routine, and that's called by the IOC to say, this record is in IO interrupt scan. What is the interrupt source associated with this particular record? And the get IOInt info routine then returns that IO scan private value that you got by calling scan IO init. So for each record, you can say this record is associated with that particular interrupt channel. And then when the interrupt happens in your interrupt service routine, you then call scan IO request with that self-same IO scan private value. Scan IO request is one of the few routines that we actually allow you to call from interrupt handlers. It takes care of queuing the request and so on, and so it's interrupt callable. So that's basically how we connect specific interrupts from hardware out to a particular records. So the device support entry table must provide that get IOInt info routine, and the interrupt handler calls scan IO request whenever the interrupt happens, and that then will result in the record being processed. In the next release of Basin 3.15, there are some slight modifications to this API. The scan IO request routine will tell you, it returns some information about about the number of priorities of interrupts that are being queued, and within your device support routine, you can then see whether you've read all the interrupts, all the records that have been processed as a result of this scan IO request. If that's useful if you need to queue data that you're getting in from hardware, then this allows you to actually do that and properly handshake between the interrupt service routine and the device support that's actually reading the actual data out of the queue. So in the future, there'll be additional features about this. So this get IOInt info routine then that you provide, it gets given a command parameter, which we'll come back to in a moment, a pointer to the record, and somewhere for you to set that IO scan private. So the idea is the routine needs to set that p private value to the interrupt source. You don't have to have called scan IO init beforehand. You can call that from this routine if you haven't created an interrupt source already. And in general, the idea is you set that p private and return 0. If you don't return 0, you can basically say, no, this record doesn't support IO interrupts after all. And if you return a non-zero value, you're basically saying, sorry, you can't do IO interrupts, and then the IOC will change the scan field to passive in that case. So this routine gets called whenever we change the scan field to or from IOInt info. So if it's just being set as turned into IO interrupt mode, or at initialization time when it's already at IO interrupt mode, then it gets called with command equals 0, and it will be called again with command equals 1 if you take it out. So you can actually have something that says, I can disable interrupts on this device because I don't have any records that are listening to this interrupt. So you can actually make use of that based on that command value if you need to. It's unusual for people to actually do that, but it is possible if you need to do that. But you would need to keep track of how many. If you have multiple records using the same interrupt channel and so on, you need to keep track of that information. That's the end of interrupts. There are a couple of, or one other thing associated with analog input and output records, which is related to converting values between engineering units and raw hardware values. There is a routine one of the device support entry routines for the AO and AI records is a routine called special linCon, special linear conversion. It's the sixth routine. It comes after the read-write. And this routine is called whenever the value of linear is changed or you change the egal and or eguff fields. That this after value, again, is also tells you whether it was just before or just after changing linear. Usually, you'd only do something in the after case. And what you need to do there is to calculate the slope of the analog conversion from the egal and eguff values and your known hardware range. So if you're a 12-bit ADC or DAC, you're going to have a different slope conversion than if you're a 16-bit ADC or DAC. And so only the device support knows how many bits there are in the actual raw hardware value, and so it has to set this eSlow field. So when the record, if that linear field is linear, then analog input record processing actually computes the engineering units val by first it adds the raw offset field, multiplies by the adjustment slope, and adds the adjustment offset. But A slow is usually 1 and A off is usually 0, so we can ignore those, and R off is also usually 0. So effectively, the raw value then gets multiplied by that slope, and we add E, and it adds E off. So we just need to set the value of that slope to know how to convert our raw value into the engineering units. And for analog output record, the processing is similar, but obviously in reverse. So this is necessary for supporting those linear conversions for analog input and output records only, though. We talked about synchronous operations. We didn't really cover asynchronous, so talk about that now. The device support is not allowed to wait if it has slow I/O. And what does slow mean? This table gives you some sort of idea. 100 microseconds is definitely a long time. 10 microseconds is definitely not a long time. And if you have a device that's somewhere in the middle, then you basically need to work things out for yourself as to which makes more sense. Bear in mind that if you block, if you delay, then you're slowing down the operations that the IOC the record processing rates that the IOC can achieve. But if you don't have a completion interrupt, then that may be a little tricky. But it's unusual to have a device that would fall into that sort of range. If you don't have a completion interrupt, then you can also do things by adding a background thread and create a worker thread that actually polls the device and waits for it to complete, and then finish off the I/O operation. So how do we actually do asynchronous I/O? Basically, this is how you decide whether you're going to be asynchronous or not, based on how long it's going to take to perform the operation. What actually happens? In a read-write operation, the packed field is used to communicate between the record and the device support, or the device support and the record, as to whether an operation is asynchronous or not. And so usually in your read or write routine, the first thing you're going to do is check the value of packed. The device support is normally called with packed set to 0, which basically is the start of an I/O operation. If it's 0, then the device support is asynchronous, so it's a slow operation. First thing it's going to do is set packed to 1, which tells the record this is going to be an asynchronous I/O. And then it starts doing whatever it is that it needs to do to actually initiate the I/O operation, either write to the hardware or send a message to its worker thread or whatever it's going to do, and then return 0. So this is how it basically tells the record, I have started an asynchronous operation. Once that operation, the hardware has come back and you've got an interrupt to say it's done or whatever, you have to arrange to run to call the process routine of the record back again, but from within a thread context, not from within an interrupt service routine. So if you have a background thread that's doing the polling, then that's fine. You can call this directly from there. If your notification comes through an interrupt service routine, then you have to use the callbacks, and we'll come back to that in a minute as to actually how to process this record. But the important lines are these three: the db scan lock, which basically says lock this record, call the process routine on the record, the PR set process routine, and pass in the record, and then you unlock afterwards. The record's process routine will, as part of its normal operation, it checks packed. So it will actually say, packed is true, I've been called back. Therefore, that must mean asynchronous completion has happened, and it will immediately call your device support read or write routine again. And that's why, going back to the top of the page, that's why we checked if packed was 0. Because if packed was 0, then we're initiating the operation, but now packed is not 0, so now we complete the I/O. We see packed is 1. We complete the I/O. We set the rval field or whatever it is that we need to do. And so that's how we basically finish off getting the value from the hardware and put it into the record and make it available for the record to do the second half of asynchronous processing. Well, nowadays, I think the argument nowadays is if you're writing asynchronous I/O, use asyn. Asyn device supports now are really remarkably easy to write with Mark's port drivers and C++ stuff and so on. So, I mean, I'm sure I could find one. I don't have one that says this is the ideal one to look at. And of course, it's going to be different for every record type because the things that you do are slightly different in the different record types. There's not much difference, but there are some subtle differences. So asyn is the better model to actually say to new writers. But a good question. But yeah, I would say the question is the ideal one is asyn, and so that's Mark River's lecture in a few weeks' time, a week or two's time, whenever that happens. So I said we actually can't call that record's process routine from our interrupt handler. And so EPICS provides a callback system which takes care of doing that for you. So we declare a callback variable, and then from within our interrupt service routine, we call callback request process callback. Actually, the priority value you can take. Often, you actually take that from the record's prio field. You don't give it a specific priority, but you can basically you can request callback processing, and that will result in this db scan lock, rset process call, and the db scan unlock again. So what this actually does is it queues a request on one of the callback handler threads. The particular thread is picked by that priority second argument, and that performs those operations that we talked about. There are, as I said, 3 callback handler threads for low, medium, and high priority operations, and usually you would use the prio field from the record for that particular argument. One of the things that we've done in actually now it's been there for quite a while, is we've extended device support. Originally, devices, basically once you've set, you set the device address and the D type at IOC startup, and you could never change it afterwards. We mitigated that. It took a bit of work, but we now have this thing called extended device support, which allows you to make changes to the D type field and or the input or output address link, the hardware address, at runtime, so that you can actually you can actually change the device you're talking to at runtime. However, you can only do this on device support that is explicitly written to support to be extended. So if you try this on a device support that hasn't been written with this extended device support in mind, then you'll find that it actually gets rejected and the values won't take. There's a description of how you do this actually in the Application Developers Guide. I think recent versions of Asyn, I know Mark was looking at implementing this in Asyn, but I'm not sure whether that's actually in or not for the extended device support. So I don't know whether you can change the Asyn, the Asyn addresses on Asyn records or not at runtime yet. I know that he's planned it, but I think it's in, but I'm not 100% sure of that. But so as I said, you can get yourself into such a situation that you can also write extended device support, which will only allow new records to be given to a device, but won't allow them to be taken away, or vice versa. You can allow records that can only be taken away and can't be added. That's up to the device support. It may be too difficult to do some of those kinds of things, to disconnect from a device or something like that. So the device support may allow you to, it may basically grab control of a record and not release it if that's too hard to write. So there's things like that the extended device support can actually do. But as we said in my response to Ron's question there, basically, if you're writing new device support, look at Asyn. It's really the powerful, flexible framework that makes it much easier to do. Definitely for message-based asynchronous devices, as indicated by the name, but synchronous devices now are also supported, and so it's worth considering that because it takes care of a lot of the boilerplate that does exist in device support.